Okay, continuing on, section 16.6 or 16.7, depending which school you're at. This talks about surface integrals. If you recall, we did that part. Surface integrals, we talked about, okay, well, am I given the description in terms of a vector or is it in terms of a function? Z equal f of x, y. So if I continue on, now we're talking about something slightly different. Given a surface S, if S has a tangent, so let me just demonstrate really quick. So let's say it looks something like this. There we go. So if S has a tangent plane at any point S except at the boundaries, then there are two unit vectors. Then there are two unit normal vectors. So think of it either this way or negative n. Either way. So if there is a tangent plane, if I could find a tangent plane, that means I could find a tangent. I'm sorry, if I could find the tangent plane, that means I could find a normal vector, because to find the equation of a tangent, I need a vector that's normal to the actual plane. Now, I want n to be a unit vector, and I'll mention why that is in a minute. If it is possible to choose a unit vector n at every point on x, y, z, so that n varies continuously over S, then S is called an oriented surface. And the given choice of n will provide S with certain orientation. So, either you're running in this direction, or you're running in the opposite direction, depending on how you're looking at this. Either you're moving this way or you're moving this way. Well, let's see. And I'll give a specific example on that. So there are two possible orientations for the given surface of n. Now, if I was given z as a function of x and y, if z equals some function g of x, y, then I could let f be 0 on one side, everything else on the other side. And I know that the normal is the gradient divided by its length. And the gradient of this, of course, will be the partial with respect to x, there it is, the partial with respect to y, there it is, and the partial with respect to z is going to always be a 1 over the magnitude of that vector. That makes it a unit vector. If I was given the description of the surface with a vector of two unknowns, then the unit normal will be the cross product of those. That's a vector perpendicular to both u and v, which is the surface, divided by its length. Now, the reason I need the length to be 1, I don't want the normal vector to affect what I'm measuring. And once I talk about what I'm measuring, I'll come back and elaborate a bit more. Definition. If I have a continuous vector field defined on oriented surface S with a unit normal, assume that you could find the unit normal, and that's going to be the key for what we're going to do. Then, unit normal, then the surface integral of f, which is the flux of f across this S, is given by, there's f, this is a vector that's oriented. And to take care of orientation, we say that is n dot ds. N takes the orientation and ds will take the length of that surface. And what would happen? Well, based on what I told you up there, if I'm given the vector in terms of, if I'm given the surface in terms of a vector, then I'm going to take the same f right there, and n would be, but I know that ds from the previous half of the section, it is the magnitude of r sub u cross r sub v times dA. Those cancel out, and I'm left with that star right there. And if I'm given the representation as a function, then I will take f, oh, I should have bolded that even more, f dotted with, and the magnitude of g divided by, and it's right there, and those cancel out, and I'm left with simply f times the gradient of g dA. Let me just talk about. Now let me elaborate on this a bit. If I'm measuring, I have a surface, and I'm measuring solar. I have a solar panel, and I'm measuring sun rays. I'm trying to figure out how much is that solar panel is gonna absorb. Well, it does make a difference whether the vector is perpendicular or the vector is coming at an angle. Of course, if it's perpendicular, I'm gonna get the most solar out of it. If it's tilted, if the sun rays are tilted, then I'm gonna get definitely less than the maximum. And by the time they are parallel, I'm not gonna get any sun rays whatsoever. I'm not gonna get out of the sun rays any power whatsoever. So, it does make a difference whether my vector field, that one too, dang it, whether my vector field is lined up, or how much is it lined up with the normal vector. And that makes a big difference. Same thing with water. If I was trying to get water across, say, an opening, I have a container, and this is the opening for the container. Well, it does matter. Is the water coming in perpendicular? I'll get the most. If the water is coming at an angle, then I'll get less. And if the water is parallel to the opening, probably I'm not going to get anything. So, bottom line, that's what it takes. And to us, it's either one of those two formulas. And on a few problems, I'll do both, just to show you how this works. So keep in mind, our general ds is simply the magnitude times dA. ds oriented, that ds right there, that is a vector. That is the normal vector multiplied by ds, which is magnitude times dA, or if it's a vector, the magnitude of cross product times dA. And notice, I do convert from S to D once I go to that area where D is the domain in which the surface is defined. So let me start with the second example. It says find the flux. They could ask you this so many different ways. Find the flux across the surface in the specified orientation. Evaluate. A lot of times they say evaluate the surface integral. That's all they say. And remember, you could use, that's the same thing. Now, n takes on the orientation and everything's normal, but n becomes, everything goes back, when I say normal, I don't mean normal as in the normal vector. I mean everything goes back to our traditional work. So here's a problem. Here's a vector field. I'm given S is part of the surface where, let's see how does that look. So I need to decide how I'm going to do this. If I could use rectangular, that's fine. If I could use parametric, that's fine. Z equal for 1, 2, 3, 4. So that's going to cause a 2 and negative 2, right? And that's going to run 0 to 4. So something like this. If I look at this sideways, that looks like a prism, right? If I look at the area of this times the height, that looks like a prism. So I have a couple of options. If I want to find flux, and they will ask for a flux, same with me on your exams, I'll always say evaluate the surface integral, and if I put it oriented, I'm going to say that is find the flux. The word flux will be there all the time. Well, let's see what we have. I have my vector field right there, okay? And S is the surface. Let me see, how am I going to describe this? Well, I could do this. I could say, well, R of X and Z is going to be, let's see how that works. I'm going to let this be X, let this be y, and let this be 4 minus x squared. That's fine. I'm using vector here. I'm using, this is not rectangular. And here what I'm going to do, I'm going to say, all right, what is r sub x? That is 1, 0, negative 2x. What is r sub y? You could use g and v, of course, if you like. I just think it's easier this way, but that's only me. That is 1, 0, oops, I'm sorry, that is 0, 1, 0. And if I take the cross product, okay, why are the letters coming out so ugly? That's going to be 0 minus 0, that is 0. The j component is also 0, and the k, I'm just getting 0, 0, 1. Wow, that is odd. Oh, let me just think about that for a sec. I see, I messed up on the I component. If you really look at it, it should have been the I component, so when I run that, it's gonna be 0 minus a negative 2x, that's 2x. The j component is actually, if you cut the middle, 0 minus 0, yeah, okay, there it is. That's r sub x, y. Okay, so how does that work? The double integral of f dot n ds is going to be, and let's see how that works. I'm going to take f. F happened to be 3, let me plug in what I have. 3y negative x squared, that's fine, and xyz, that is xy, and in place of z, that's the only substitution I have to make. And let me just take this, close it a bit, and put it right there. And I'm going to dot that with what? I'm going to dot that with n. Well, in this case, I got, this is, well, that's not n really. That's a normal, but I need it to be a unit normal. Well, if I put everything together, that's simply 2x, 0, and 1. So I don't need to derive this every time. Divided by its length times the length. I'll go straight for this. Dot it with the cross product. There's the cross product. dA. Alright, well, how does it work? dA is going to be what? If I look from the top down, what do I see? I see x running from negative 2 to positive 2, and y running from 0 to 4. There it is. So basically, that would be, if I multiply those, that's 6, that would be 6xy plus 0 times x squared is 0 plus 1 times, so 4xy minus xy cubed. There it is. dy dx. That's a really nice integral to work with, and that's all there is to it. And that'll work. Now, I could have done this problem slightly different, and let me elaborate. Again, it's up to you. I could have said the double integral of n dot ds over s, I should say, is going to equal the double integral over d, and let's see how this works. I could have said this is actually 3y, this is negative x squared, and this is xy into 4 minus x squared, one shot, right? And I'm going to dot that, and hey, look. All what I have to do is get this to be z plus x squared minus 4 equals 0. Make sure you get a 0 on one side. That's your g. And take the gradient of that. What's the gradient of that? The gradient of that would be 2x, 0, and a 1 dA. Right? And I could do the same thing. dy dx. X runs from negative 2 to 2, 0 to 4. That will work. And what would that be? That would be 6xy. That's a 0 plus. And did you notice that we got the same exact thing? which is quicker? Well, you figure that out during the homework. That should be x cubed y, right? Not xy cubed, guys. So, practice on the homework and get those out of the way. There are really very limited amount of problems you get. The variation is not that great, you know. It's not like you get problems out of the blue. You glance at a problem and you'll figure out when you could do rectangular. If it's a prism, it's not that bad. But if it's not a prism, if it's a cone, then you really need the vector presentation. Speaking of, what do we have? The surface here looks like a paraboloid. That's not a prism. And I'm cutting that at 1. So the shadow on the floor is actually x squared plus y squared equal a 1. Okay, no problem. F is right there. That really doesn't change much. But what really affects this, how am I going to figure out my normal vector? So here, R of u and x, or you could go x, it's up to you. I'm going to go u and v is going to be, let me think, if it equals to 1, then that's going to be u the sine of v. Oops, u the cosine of v, my mistake. U the cosine of v, u the sine of v, and this is going to be, if I take this squared and this squared, I'm going to get u squared. If I'm not mistaken, that's what it is, right? Yeah. So what I need now, r sub u is going to be the cosine of v, the sine of v, and 2u. R sub v is going to equal negative u the sine of v, u the cosine of v, and 0. And if I take r sub u and cross it with r sub v, what I will get, the I component will be 0 minus 2u squared the cosine of v. The j component will be 0 minus a negative plus, but it's always take the opposite. 2u squared the sine of v. And the j component would be u cosine squared plus u sine squared, which is u squared. We did that too many times. And now you would say the double integral over s of f dot n ds is going to equal the double integral. And let's see how that works. What is x? In this case, x is u the cosine of v. There is no j. The k is y. The k is u sine of v. And you're going to dot that with what we got. Negative 2 u squared cosine of v, negative 2 u squared sine of v, and u squared. And let me shrink this a bit. Give it a sec to register. There it is. And shift it a bit to the right. And how is that going to work? Well, I noticed that I didn't write it. I noticed that we're talking about a unit circle, right? Circle with a radius of 1. Wouldn't that be 0 to 2 pi? And 0 to 1? And I could run what? I'm going to have to convert. So if I convert those, that would be what? When I said this, u varies between 0 and 1, and v varies between 0 and 2. There you go. du dv. And that will do the trick. So convert from rectangular to the actual, and there it is. Now rectangular, and this will be very challenging, because to describe the surface, this is not a prism. That's a bit more challenging than we like. And if I look at the next problem, now we're looking at a cone. The same thing happened. Well, a cone looks like this. And again, I'm not going to have options with cones because it's not a prism. So this one, actually, the cone looks like this. It's this part of the cone, where this is 1, this is 4. On the floor, That looks like that. So in this case, what do I want? Well, they already gave me an z, told me what that equals. I know how that works. So I'm going to go automatically for r. You could go for r and theta if you like. You could go for u and v. The book likes u and v, whatever makes you happy. So this is going to be u the cosine of v, u the sine of v, and this is going to be just u, right? Right. And I'm going to take r sub u, and that is the cosine of v, the sine of v, and 1. And I'm going to take r sub v, and that's going to be negative u the sine of v, u the cosine of v, and a 0. And we just did that. R sub u cross. So you'll notice a lot of repetitions. That would be what? If you remember, that is 0, negative u the cosine of v, negative u the sine of v, and just u. And there it is. The double integral over s of f dot ds, or d rho, picks up the n. What is n? Well, that is f. What's f? The y component, that is u the sine of v, negative x, negative u the cosine of v, and k is just 1. Dot it with what I just got right there. And that's going to be negative u the cosine of v. I'm going to shrink that a bit more. Again, we do that a lot. Oh, come on. And I need to convert the rectangular into the u and v kind of like polar stuff. Okay. Negative u the sine of v and u, and du dv. V runs from 0 to 2 pi, and u run from 1 to 2. And again, try to describe this with rectangular coordinates is not wise. Sometimes you can, most of the time you're better off leaving it as is. One more to go, and this one I'm going to do 2 different ways. So we have a sphere. You know, we're not going to leave a sphere out. We want to touch on all subjects. So we know how a sphere looks like. You could use spherical coordinates. We're talking about this part of the graph, you guys. We're talking about the bottom half of the sphere. Now, something I have been kind of not pushing. Outwards is positive orientation. Outwards is positive orientation. Downwards, if it's downwards, you just put a minus in front of this, and that does the trick. And you notice this says downwards. So that's how you're measuring those. Well, let's see what S is. S is the hemisphere, so the bottom half. So it looks something like this. In which this is 3, 3, 3, 3, and that's a 3. Right? So it's better to do it this way. I can never get it straight that way. There. And then put the axis on it. Something like that, right? Where this is 3, this is 3, and that is 3. Well, we know how to do this. We say, well, okay, look, we know that we're looking at r of theta and phi, and we don't like it, but we know how it works. That's going to be a row 3, the cosine of theta, sine of phi. 3, the sine of theta, sine of phi. And 3, the cosine of phi. Okay, that's, we could take r sub theta. We did that already. We know how long it is, but no problem. That's going to be r sub theta, negative 3, the sine of theta, sine of phi. 3, the cosine of theta, sine of phi, and a 0. and r sub phi, which is going to be 3 the cosine of theta cosine of phi, 3 the sine of theta cosine of phi, and negative 3 the sine of phi. And you know the drill. We're going to take r sub theta crossed with r sub phi, and that's no fun. That is the I component. That will be those 9 the cosine of theta sine squared of phi minus 0. So that's good news. Negative, the middle, that's going to be 9 the sine of theta sine squared of phi minus 0. Okay, very good. Got it. And if I go for the j component, that's the last component, I will be looking at 9 the sine squared of theta sine of phi cosine of phi. That will be this minus 9 the cosine squared of theta cosine of phi sine of phi. Again, a massive mess. So I'll clean that up just a bit. Maybe I should use theta and beta next time. So that is 9 the cosine of theta sine squared of phi. This is negative 9 the sine of theta sine squared of phi. And here, if I factor a 9 sine of phi cosine of phi out, I will have a sine squared. What's this, a minus? The last one. Negative minus a negative. They're both negative. So if you take a negative, that's sine squared plus cosine squared, which is a 1. Still not that pleasant. Okay, well, then what? Then here I'm going to say the double integral of f dot n ds is going to equal the double integral. And how does that work? Well, y squared, you go back to the original, remember, the original setup. So y squared, that is 9 sine squared of theta sine squared of phi minus x squared negative 9 the cosine squared of theta sine squared of phi plus 3z. 3 times 3 is 9 cosine of phi. Alright, I'm going to dot that with this mess. 9 the cosine of theta. A lot of things will cancel out, you can imagine. Negative 9 the sine of theta sine squared of phi, and negative 9 the sine of theta cosine sine of phi cosine of phi. Now, how does that work? We forgot to mention, we have theta running between, if I convert 0 to 2 pi, and phi runs, remember, phi equals 0 starts right there, so it's going to run from pi over 2 to pi. And there it is. Oh, I forgot. Oh, actually, I didn't convert. I don't need the rho squared. That's it. Okay, now, watch. You might be thinking, well, this is good. We could get it to work. Yes, we can. But look. You guys, can't I say z equal negative the square root of 9 minus x squared minus y squared? Because that's the bottom. And can't I say z plus the square root of 9 minus x squared minus y squared equal, or you could move the z over, make them both negative. It makes no difference. Bottom line, that's my g. And I could say the double integral of f dot n ds is going to equal the double integral, and let's see how that works. I'm looking at f, which is y squared is fine. That's Negative x squared is fine. 3z, that's 3. And what is z? We just figured out that z was, where did I write it? Oh, right there. Z is negative the square root of 9 minus x squared minus y squared. Alright, dot it with what? Dot it with the gradient of this. Isn't that 1 over twice the square root of 9 minus x squared minus y squared times negative 2x? And so those cancel out. The partial with respect to y is the same but with a y. And the partial with respect to z is just a 1. dA. Well, the hard part is coming up with the limits, except if you multiply those, you'll notice that's negative xy squared over the square root. And can you guess what we're going to do? Plus x squared y divided by the square root of 9 minus x squared minus y squared minus 3 the square root of 9 minus x squared minus y squared. Let me make sure I did that correctly. Okay, that's good. dA. And how do you think we're going to work that out? So remember A. A is a circle with a radius of 3. Well, that is the double integral. If I combine those, that is 9 minus x squared minus y squared underneath the radical. So those combine, that's negative x y squared plus x squared y. And if I multiply that minus 3, 9 minus x squared minus y squared dA. And I could sit over d, of course, where d is that domain. So we're looking at a circle with a radius of 3. That's, oh, and it was downwards orientation. I forgot about that. And what would that be? Well, that would be negative r the cosine of theta, r squared the sine squared of theta, mine plus r squared cosine squared of theta sine of theta, minus 3 times 9 minus r squared, that's this part, over the square root of 9 minus r squared, right? Here I did convert. So when I described the surface using what do you call them? When I described the surface using spherical coordinates, I didn't pick the rho squared, right? Because I didn't convert. Here I did convert. And if I convert, what does that mean? That means I'm going to pick an r d theta. And r runs from 0 to 2 pi. And theta runs from, 0 to 3. And there it is. So again, which is easier? Well, that depends. Some students would rather do the rectangular. Now, when they give you rectangular, numbers work out nicer. Since I'm making those up, they're not coming out as nice. And that concludes this section.